Well, hello and welcome to today's webinar. We'll be presenting a recent study between Lawrence Berkeley National Lab and the Brattle Group describing building sector decarbonization solutions and how they complement the speed and scale of power sector decarbonization. Before we begin today, I just have a few housekeeping notes and reminders for you all. First, we're asking you to please share any questions that you have in the Q&A box, which is located in the Zoom controls panel. We encourage questions throughout the presentation, and we'll leave time at the end to address them after we finish the main content. Second note is that we'll be recording this webinar, and we're going to post it on our research website. We'll send a link to the recording to all the webinar registrants so you have it available. And then last, we've got a high-level summary of this study, as well as links to the specific research article, supporting data and visualizations at a website, which we'll add to the chat box so you can access that later on for reference. So with those housekeeping notes out of the way, it's my pleasure to introduce our three presenters and lead study authors of this work. So first, Jared Langevin is a research scientist at Lawrence Berkeley National Lab, where he models the national impacts of building efficiency on long-term energy use and carbon emissions, as well as developing decision support algorithms for energy flexible building operations and researches human building interactions. Based in Washington, D.C., Jared was previously a Science and Technology Policy Fellow at the U.S. Department of Energy's Building Technologies Office, where he co-created BTO's SCOUT program for National Building Efficiency Impact Analysis. Jared has a PhD in architectural engineering from Drexel University. And before entering into his graduate studies at Drexel, Jared received a bachelor's degree in architecture from Carnegie Mellon University. We're also joined by Avin Satra-Malloy, who's a computational research scientist in the Building Technologies and Urban Systems Division at LB&L. In this role, he conducts interdisciplinary research and analysis to support energy policy and technology development for the U.S. Department of Energy Building Technologies Office. Avin received his PhD from the University of Oxford's Environmental Change Institute, and his research there focused on applications of advanced computational methods to high-resolution electricity consumption and occupant data, especially to identify opportunities for further efficiency and flexibility in the energy system. And we're also joined by Ryan Ledick, who's a principal at the Brattle Group, specializing in regulatory and planning matters related to the emergence of distributed energy technologies. Ryan has consulted for more than 80 clients across 35 states and 9 countries. He supported clients in matters related to energy storage, load flexibility, distributed generation, electrification, retail rate design, energy efficiency, and grid modernization. Ryan's quite prolific, and his work has been cited in regulatory decisions around procurement targets for energy storage and demand response, as well as work authorizing billions of dollars in smart metering investments and approving the introduction of innovative rate designs. Among his notable publications are Saudi Arabia's first demand-side management plan and the Federal Energy Regulatory Commission's landmark National Assessment of Demand Response Potential Study. Ryan has a master's in management science and engineering from Stanford University. So thanks for joining, and we're going to go ahead and get started here. I'll pass the mic over to Jared to present the content.
Great, thanks so much, Andy. So in the next hour, we're going to present a range of insights about U.S. building sector decarbonization that I think will feel both familiar and new at the same time. Familiar because to some degree, all of us are experts on buildings and building decarbonization. We all live and work in buildings, and I think intuitively we kind of understand that the energy that it takes to keep those experiences humming along has to be addressed if we're going to decarbonize the U.S. economy. But I think our results will also feel new because it's been hard to put a quantitative point on what building sector decarbonization might actually look like and the implications for broader net zero by 2050 emissions pathways. And that's the crux of what we're trying to do with this study. So in this work, we sought to quantitatively map out those futures for the U.S. building sector and decarbonization of the sector through 2050, and to do so in a holistic way. So yes, how buildings decarbonize is going to be strongly influenced by how fast we decarbonize the power sector and electrify building loads. But we also represent that interaction in the other direction. So what we do to change patterns of building demand through energy efficiency, through demand flexibility, and through electrification can influence the energy supply. And it's important that we start capturing that dynamic better. And so our two headline findings reflect that kind of bi-directional focus. So first, Our modeling shows that we can achieve deep reductions in building sector CO2 emissions up to 91% by 2050. And we can do that with aggressive action on both the demand and supply side of the energy system. And then second, we show that demand side efficiency and flexibility in buildings can avoid up to over a third of the cost of decarbonizing the power sector, or over $100 billion annually by 2050 in absolute terms. And then there's this more nuanced story about how all these impacts could actually play out in practice. So first there we show that our deepest emissions reductions are strongly dependent on energy efficiency and electrification deployment on the demand side, and that these demand side measures can provide up to almost half the overall emissions reductions we find in our study by 2050. We explore the policy-related levers that could make that increased demand-side deployment happen. And we find that codes and standards are kind of a key lever for emissions reductions by 2050, while early retrofitting can have a more significant influence on near-term emissions and overall kind of carbon budget between now and 2050. And then lastly, we generate insights about the timing of demand-side emissions impacts in buildings. And so in particular, we see strong potential for energy efficiency to reduce emissions in the near term, while the grid is still decarbonizing, and then to enable later reductions from end-use electrification under a decarbonized grid. So let's dive into this further with a survey of the emissions landscape for the energy sector. And so I think this EIA plot nicely illustrates that the residential and commercial building loads that we're focused on in our analysis are together amongst the largest sources of end-use CO2 emissions from the energy sector, so about 35% of those emissions. So that by itself should place a huge focus on buildings as a part of economy-wide decarbonization. And of course, that doesn't consider the many non-emissions benefits of decarbonizing buildings to energy bills, quality of life, integration of other low-carbon technologies, and so on and so forth. But in much of the energy system modeling and economy-wide decarbonization studies that we surveyed to date, we found that the representation of buildings and changes in building demand is rather limited and kind of obscures the big contributions that buildings already make now to electricity demand and emissions, for example, which you can see again in this figure. And so much of the burden of decarbonization in this work falls to the supply side and the power sector specifically. And so a key goal of our work is to bring the demand side, and specifically demand side measures for building decarbonization, into the fold of these larger kind of modeling and decision-making exercises and conversations. So let's take a look at the building measures that we represented in our analysis, and we'll start on the left-hand side of this slide. So we have three measure features that we focused on. We looked at end-use electrification, or EL in the presentation, and that's converting fossil-based heating, water heating, and cooking to electric service. We also have energy efficiency, or EE, which is kind of persistent reductions in energy use that we apply to both electric and non-electric loads. That includes, both equipment improvements, but also improvements to the building envelope and controls. And then lastly, we have demand flexibility, or DF, which entails load shedding and shifting in a way that's advantageous from the grid perspective. And generally in our analysis, we're representing flexibility as being packaged with energy efficiency and electrification measures. Across those measure features, we represent three tiers of cost and performance, above and beyond what's represented in our reference case, which is based on the 2021 EIA annual energy outlook in terms of the building demand projections. So we have a performance guidelines tier. That's the latest Energy Star, IECC, and ASHRAE 90.1 specifications, and we escalate those over time to match reference case rates of change. We also have a best available measure tier. So among the highest performing and generally highest cost measures available on the market today, with performance and costs again kind of escalated to match reference case rates of change. And then lastly, we have a prospective measure tier, which represents target performance and cost characteristics that are drawn where possible from existing roadmaps or are otherwise developed to meet aggressive paybacks at a high performance level. And so these are measures that enter the market later and serve as the basis for what we call a breakthrough technology menu that kind of serves as a ceiling for what's available on the market in terms of performance level. So our analysis workflow runs primarily through two modeling tools. On the demand side, we have the Scout model, and on the supply side, we have Brattle's GridSim model. And so I'll just work through the analysis flow here briefly. So starting at left, we have our set of building electrification, efficiency, and flexibility measures. We also have a few other key inputs that include external scenarios of electrification that were developed by Guidehouse. We have the reference case buildings forecast from EIA, and then we also have Brattle's power system forecast. So we run those inputs through 12 scenarios of measure deployment and supply side change that cover the years 2023 to 2050. And that includes looking at measure impacts in isolation as well as with overlaps and kind of portfolio level dynamics considered. And then we pair electricity demand projections with Brattle's grid forecast and fossil building demand projections with EIA emission factors to arrive at the emissions impacts in 25 grid regions covering the contiguous US from our various scenarios. There's also a cost assessment portion of the flow here. And so this involves assessing both individual and portfolio level measure deployment costs, along with the impacts of the measure portfolio on power system costs in 2030 and 2050. So the 12 scenarios that we ran are organized around 3 benchmark scenarios, and these represent low, moderate, and aggressive decarbonization. Those are outlined here, and then the remaining 9 scenarios are kind of serve as sensitivity cases. So the scenarios are generally defined by 3 dimensions. They're defined by 2 dimensions: the level of efficiency, flexibility, and electrification deployment on the demand side, and then the level of grid decarbonization on the supply side. So our low case assumes, for example, aggressive electrification without a parallel focus on efficiency on the demand side, alongside a power grid that decarbonizes more slowly, which is consistent with Brattle's GridSim reference case, and that represents only the effects of policies that are on the books now. And then our moderate and high cases both introduce a parallel focus on increased efficiency deployment alongside moderate to high electrification, with, on the grid side, 80% grid decarbonization by 2050 in the moderate case and 100% by 2035 in the aggressive case, respectively. And you'll note here from the table that higher progress on the demand side generally corresponds with higher levels of electrification, which are driven by a variety of market, regulatory, and technology factors that Guidehouse considered in their analysis. The demand side deployment is also driven by the introduction of more stringent building codes and standards, and the introduction of building technologies which with breakthrough cost and performance characteristics, as I mentioned earlier, as well as the representation of measures that enable demand side flexibility alongside efficiency. And so we're glad to get more into the details of those scenarios later, but for now, I think we should just keep in mind the thrust of what we're investigating here, which is, a case with high electrification but no efficiency and slow grid decarbonization. So that's the low case. A case with additional efficiency and electrification at levels you'd expect mostly from market-based instruments like incentives and technology improvements, with deep but not complete grid decarbonization. And then lastly, a case with high progress on both the demand and supply side that helps us understand, really the potential depth of building sector energy and emissions reductions by 2050. So let's get into our findings, starting with the magnitude and drivers of overall building emissions reductions. And so again, here we're finding potential for deep emissions reductions in 2050 and highlighting codes and standards and early retrofits as key deployment levers. So the first thing we looked at here was the trajectory of total building energy related CO2 emissions, which is on the left side. Site energy use for buildings for the whole sector, that's in the middle here. And then electricity use at right from now to 2050. And you'll see here in our reference case, we have declining building emissions, which are driven strongly by declining power sector emissions, since buildings consume about 75% of power sector demand. And that they're responsible for about 75% of power sector demand. And those declining emissions stagnate around 2030 out to 2050. So all the while, energy use in the middle plot here and electricity use on the right are increasing slightly, with lots of new building additions that are only partially offset by some improved efficiency in the baseline here for the building sector. And so this is what we expect in the absence of further decarbonization efforts for the building sector. Now we examine a set of scenarios that where we really push end-use electrification of buildings, but without efficiency, and the grid decarbonizes slowly. And what we see as a result is, true to the scenario name here, the lowest level of energy and emissions reductions across our scenarios. And on the electricity side of things, at right here, we can see that high electrification is leading to increases of up to almost a quarter of the reference case building electricity use by 2050. So the highest increase there represents a side case we ran where high electrification is occurring inefficiently with lots of resistance-based heating and water heating deployment. And so we see that has real implications for the additional amount of electricity that the grid needs to serve. In the moderate set of cases, we're introducing more efficiency and flexibility alongside electrification, and the grid is decarbonizing more deeply, but not completely by 2050. So this results in larger overall emissions reductions at left, as well as larger but more variable energy reductions in the middle, and a pretty wide range of outcomes for electricity. So you can see we range from reducing electricity versus the reference case to increasing it by 2050. The best cases across the board here involve efficiency with some early retrofitting behavior assumed. And the worst case here is where electricity is increasing, involves electrification only without parallel efficiency deployment. And then in the last kind of best case set of scenarios, we see these same kinds of trends as in the moderate case, but amplified as we have more aggressive demand side electrification and efficiency and full grid decarbonization by 2035. So these cases give us the largest emissions reductions, and the one with early retrofitting behavior assumed gets us to that 91% reduction result that was highlighted earlier. Our energy reductions are also generally deeper, but even more variable across scenarios. And then electricity again ranges from decreasing to up to 11% by 2050 in the best case to increasing over the reference case by 2050. And again, the latter occurs in a case where we have only high electrification without parallel efficiency. So if we put all this together, we see a really wide range of possible futures that include some sometimes conflicting trends across the different metrics. One thing we were particularly interested in was benchmarking the emissions that remain in 2050 against the notion of kind of achieving net zero emissions economy-wide by 2050, considering remaining emissions plus offsets. So if you take literature estimates of available offsets of emissions in 2050 from land use sinks and negative emissions technologies, and you just allocate that proportionally to buildings' contribution to economy-wide emissions, you get something like 400 megatons of CO2, and that's just above the results for our most aggressive case, as you can see on the left here. So in theory, this level of remaining emissions might be compatible with net zero by 2050 with that kind of target, but there's a lot of uncertainty and kind of messiness about the level and allocation of emissions offsets, and it's going to take much more cross-sectoral modeling work to figure that out with more confidence. I would like to highlight that getting to these most favorable scenarios is not a given, and it requires a real acceleration and progress starting now. So I've just provided some stats here for our aggressive benchmark scenario on the three pillars of electrification. So the number of heat pump deployments, on efficiency, that's the number of envelope retrofits, and then smart controls and flexibility. So that's the penetration of platforms that enable advanced controls in our modeling. I won't go through all the numbers in detail, but we do benchmark these in the paper. And in general, these are big numbers that represent huge increases in progress over what we've been seeing. So a stark visual indication of this is shown at right with the cumulative number of residential heat pump sales, and also including heat pump water heating here across various scenarios. The heat pump results are shown in red, the water heating is shown in blue, and the solid lines here are historical trends going all the way back to just after 2000. The dashed lines are reference case projections, and the shaded regions are the range of results across our scenarios. And so you can see that there's just a dramatic departure that needs to start happening right now to get to our most favorable building sector futures in 2050. So we know the challenges ahead, and we try to use our data to highlight some of the key levers that decision makers can use to push these levels of demand side measure deployment in buildings. And these plots give us kind of a snapshot of annual emissions reductions from our demand side measures in 2050 across the full 12 scenarios that we ran. And we looked at how playing with some of these levers in the modeling impacts emissions reductions from those three benchmark cases, the low, the moderate, and aggressive cases, which are shown as dark blue bars on the plot here. I'll just highlight two things that jump out here. The first is the strong influence of the levers we include that relate to additional deployment of energy efficiency versus the reference case. So introduction of breakthrough efficiency measures, elevated codes and standards, and then representing additional efficiency and flexibility measures on the market that aren't in the reference case. And whether you're looking at moderate or aggressive deployment scenarios here, you can see that failing to do these things is substantially is precluding much of our emissions reduction potential, 41 to 58% of that potential for the benchmark cases. In particular, we find that codes and standards seem to be especially important for getting efficiency into the market, and in relative terms, they are the most impactful under more moderate scenarios where buildings are electrifying more slowly, and increased efficiency deployment can provide something of a hedge against slower electrification. So that's the annual impacts in 2050. If we look at the same plot, but then on a cumulative basis, so the total emissions reductions in our scenarios summed between now and 2050, we see something of a different hierarchy in the results. And in particular, this is where the effects of assuming early retrofitting behavior, so that's replacement before the end of life of building equipment or components, really starts to shine through as the most impactful deployment lever across both the moderate and aggressive scenario conditions. And I think that's important to note here, because while our emissions targets are based on 2050, I think we need to be mindful of the overall budget of emissions that is consistent with more manageable scenarios of climate change, and pulling these levers that can begin reducing emissions from buildings deeper and sooner is really beneficial and critical. And so with that, I will throw it to Avon.
Great. Thank you, Jared. Hi, everyone. Thanks for that high-level overview of the study findings and looking at some of the primary levers that we explored in our model. And next, I'm going to take us through some of the more detailed findings from our study, including a more detailed look at attributions of building sector emissions to different types of technologies, and also comparing across demand and supply. And these two findings really highlight the importance of the complex interplay of different types of measures in our analysis, and some of the insights there. So if you go to the next slide, please. So first, we can look closer at how building sector emissions are reduced across both demand and supply side, and then attribute building emissions reductions to specific end uses. This kind of result really helps us understand the different types of building technologies or operational approaches that we should target, and also the end uses that have the highest potential for emissions reductions. This figure returns to our three benchmark scenarios here, and we are plotting emissions reduction wedges, which will be familiar to many of you. The dashed line in each of these plots represents the reference case building CO2 emissions that Jared was showing previously. And the colored wedges below that line are end-use level reductions from our demand-side building measures. There's also a dark gray wedge below the colored wedges in both the moderate and aggressive decarbonization cases, and that represents the emissions reductions that we attribute to additional grid decarbonization in those two scenarios. So one thing I'd like to highlight in this figure is that when we look across the different demand-side end uses, we find that in the most aggressive decarbonization benchmark, these wedges contribute up to nearly half of emissions reductions in 2050 in this most aggressive decarbonization scenario, with the rest of the emissions reductions in that scenario attributable to additional grid decarbonization. We also see here that the measures that target HVAC and water heating equipment are really making the largest contributions to overall reductions. In the low scenario, where we only focus on equipment electrification, you see HVAC and water heating, and there's a very small sliver there that is for cooking electrification. Those are the only measures that show reductions in that scenario. So this is the kind of figure that gives us insights into the end use attribution of emissions reductions. What we're looking at here on this slide, then the next slide, is what we call a waterfall plot. Again, a pretty classic figure for decarbonization. And this shows the results for our aggressive decarbonization benchmark scenario. And what this plot enables is for us to look at the emissions reductions across different categories or measure types instead of just end uses. So I'll step through each of these in turn. So starting with the bar on the left here, we use 2005 as our reference point. And in 2005, building CO2 emissions were around just under 2,400 megatons of CO2. Moving forward, the next segment there shows historical emissions reductions up to 2022, which is a significant amount of savings. And that's mostly driven by energy efficiency, keeping demand growth relatively flat during those years, but as well as the electricity system becoming cleaner in the US. The next segment shows additional emissions reductions out to 2030 that are modeled under this Brattle reference case. And again, I think Jared mentioned it, but the Brattle reference case assumes the impact of policies that are on the books, such as state renewable portfolio standards that help reduce emissions from the grid. So that's where you're getting emissions reductions in the reference case there. The next segments, those segments in light green and teal, show the impacts of the measures in our analysis and the savings that are attributable to additional grid decarbonization out to 2030. And what we find is that the efficiency reductions, which are split across both electric and non-electric efficiency, are around 1.6 times larger than the electrification reductions in the early years of our modeling time horizon out to 2030. The grid decarbonization segment there is particularly large because this scenario, I'll just remind you, assumes that we're achieving a 100% reduction in grid emissions intensity by 2035. So there's a lot of emissions reductions from the power sector as that is rapidly accelerating to a zero carbon power system by 2035. It's on a very accelerated timeline. But what we find in 2030 is that the total building sector emissions are 815 megatons of CO2, and that's a 65% reduction from 2005 levels. If we continue down the waterfall, we see that there's a small amount of reference case emissions additions actually after 2030, and that's driven in part by some of the phase out of the policies that were modeled in the reference case out to 2030. But the key thing to point out here are the segments representing the building measures. And we see here the clear differences between the near term and the long term, because in the 2030 to 2050 time horizon, the electrification impacts grow and are around 2 times the magnitude of the electric and non-electric efficiency measures. And this is driven in part by the gradual ramp up of load electrification in our modeling, and also this the power sector achieving its full grid decarbonization by 2035. But also one thing that we represent in this case is the market entry of very high performing building technologies that enter the market in 2030. And those are contributing to that larger EL plus DF segment in this figure. And so what we find in this scenario in 2050 is that the total building sector emissions reach 262 megatons. And this is 89% below 2005 levels. And just a reminder that our most aggressive scenario did show 91%, and that's just a sensitivity case that improves a few of the parameters in that portion of the analysis. Okay, so the figure that we're showing here is one that breaks out these remaining emissions by the contributing end uses and building sectors. And what we find here is that the remaining emissions are relatively higher in the commercial sector, and mostly that's attributable to residual thermal end uses such as heating, cooling, and water heating emissions. But there's also this considerable segment of non-electric fossil-based other energy use that is attributable to commercial buildings. This segment includes things such as emergency generators, combined heat and power, and manufacturing performed in commercial buildings. So we have some insight into what that other consists of, but we didn't represent in our modeling measures that were necessarily able to affect and reduce that energy use. If we compare the remaining emissions from our aggressive decarbonization case to those from the moderate and low decarbonization cases, you'll see, of course, that there are much more diverse sources of remaining in emissions in 2050 due to both less aggressive building decarbonization, but also the grid decarbonization is not as aggressive in those scenarios either. And still, we see that remaining emissions are primarily driven by residual thermal loads that do not switch to electricity. Okay, and this slide will be the last that I present here. And there's a lot of information contained in this figure. It's one of our favorites. It's called a sunburst for folks who aren't familiar with these figures. But it really just highlights the bottom-up nature of our modeling framework. So because we use a bottom-up modeling framework, we can really go deep into the segmentation of emissions reductions that we're modeling to give researchers, policymakers, any other sort of stakeholder more granular details that could be useful for program design or for policy design. So I'll briefly just discuss the key features of this figure, but what you'll find here is an interactive link that's published alongside many of the results figures that were shown today that you can explore, and you can also download data on your own to play with. And we certainly encourage you to do that. So in this visualization, we're segmenting 2050 emissions reductions according to 4 levels. So we'll start with the innermost ring there, where those colors represent the different regions in our analysis, and those are aggregations of the 25 EIA electricity market module regions. There's a map there that shows the regions. The second ring is the building type, where we look at 2 residential and 8 different commercial building types. The third ring is the building end use, and the fourth is the measure type, where that's applicable. So for example, if the heating end use that you see there, that pink wedge in the third ring is representing heating savings, and we attribute those to all 3 different types of measures that in our analysis. So that's electrification, non-electric efficiency, and also electric efficiency. There are other end uses like PCs and electronics that, of course, are only affected by electric efficiency, and so they're not broken out on this 4th level. The segments are ordered in each level clockwise by the share of total CO2 emissions reductions that are attributable to each of those segments, and then you'll see a lot of white in the plot, and those white segments contribute less than 0.2% of total emissions reductions. Okay, so that's an orientation to the figure. And again, you'll definitely want to follow that interactive link, and we can put that in the chat and you can explore on your own. But if I was just to kind of summarize some of the key findings here, when considered across the full building sector in 2050, emissions reduction opportunities we find are strongly weighted towards single family homes in highly populated regions with large heating and cooling service demands, and also higher reference case electricity system emissions. So in particular, that's the Southeast and also the Great Lakes and Mid-Atlantic. And within these region and building type segments, the most substantial shares of 2050 CO2 reductions come from heating and water heating electrification. So that's just one example of one of the key insights that arises from more granular investigations of how these building sector emissions are reduced across each of our scenarios. And comparing these figures for different scenarios, so for instance, the low versus the aggressive, and also looking at different years, such as 2030 and 2050, and you can do all of that using the interactive version of this figure. That provides really important insights, and we do hope you'll spend some time with these figures after the talk. Okay, with that, I am going to hand it over to Ryan, who's going to speak to the supply side aspects of our research.
Great, thanks, Avon. I could stare at those sunburst charts all day. They have almost a hypnotizing effect on me. But now, as Avon said, we will turn to the supply side or the power sector portion of this presentation. Jared and Avon have given a really nice overview of what's happening within the buildings in terms of emissions reductions and energy impacts. We also, with this study, wanted to dig into what's happening in the power sector. As you probably got from Jared's and Avon's comments, there's a lot happening on that side of this analysis, right? There's a lot of power sector decarbonization that's happening in order to make sure that the electrification pathway has decarbonization benefits. And there's also a lot of power generation that just needs to be built to serve all of that new electrification load. So with this portion of the analysis, we really dug into that, and in particular, wanted to understand what the cost of all of that power sector development would be, and then what the impact on those costs would be from these new efficiency and flexibility measures that have been introduced in the study. So first, I'll just kind of, at a very high level, try and walk you through how we modeled this interaction between the power sector and all of the building modeling that Jared and Avon just presented. The first step here, as they mentioned, was to define our supply side scenarios, that reference case, and then the various decarbonization cases. Once we had clearly defined those scenarios, then we used Brattle's grid sim model to forecast what the marginal system costs and emissions would be associated with each one of those scenarios. And so as you probably figured out from the earlier comments, GridSim is a model that if we give it as input information about what we expect demand for electricity to be in the future, we characterize the existing power generation fleet, and then also tell the model which power generation options are available to it to add to the system over time, and what the cost of those power generation options are, and then also what the various policies are that will be in place that relate to decarbonization or other factors. The model is then able to simulate over a multi-decade time horizon what the cost minimizing additions of those resources would be, and then at an hourly level, how all those power generation resources would actually operate in order to make sure that demand for electricity is being met by power supply in each hour. So we use GridSim to forecast those, if we could just stay on that chart for a second. We use GridSim to forecast those marginal system costs and emissions. We then take the hourly energy efficiency and demand flexibility impacts that Jared and Avon just presented, combine those with the forecast of marginal costs in order to estimate the gross benefits of each demand flexibility, energy efficiency, and efficient electrification measure. And then ultimately, as a last step, compare those gross cost savings benefits of those demand side measures to some estimates of the incremental cost of each of those demand side technologies in order to develop an overall aggregate view on both the gross benefits and then how those gross benefits relate to the costs of the efficient portfolio that we've analyzed. So that's just an overview, and there's obviously a lot more detail in our approach in the report. So we did look at 3 modeling cases. The reference case, as you heard, is defined just by existing renewables or decarbonization policies, nothing new. So that's largely state RPS mandates. And then in terms of electricity demand growth, our reference case is characterized by a minimal amount of new electric vehicle adoption. 8% of light duty vehicles would be electric by 2050. And just sort of a minimum baseline amount of building electrification. Then we have the 80 by 50 case. Here, we are telling the model, forcing the model to reduce carbon emissions from the power sector by 80% relative to 2005 emissions levels. And we're also in this scenario building in a lot more electrification. So we have by 2050, 95% of light duty vehicles being electric, 50% of medium duty, and 35% of heavy duty. At the same time, we also have what we've characterized as inefficient electrification happening within buildings for heating and other energy end uses. So with this case, we have both decarbonization on the power side, and then also a significant amount of new load. And then with the third case, which we're calling the 100 by 35 case, we're taking that even further. We're requiring that the power sector be carbon-free by 2035. We're using those same, fairly aggressive transportation electrification assumptions, and then we're assuming that inefficient electrification of buildings is happening faster to the point where we have a 23% increase in building load relative to the reference case by 2050. So that's how we've characterized those 3 scenarios. And now what we're showing you in these charts is just the amount of generation capacity that is online in each year in each of those 3 cases by year. And so what will jump out at you in these charts is if we just focus on the left-hand chart, the reference case, what you can see is that the amount of generation capacity that's online in 2050 is about 1.5 the amount of capacity that's online in 2020. So about a 50% increase in capacity will be needed in that reference case scenario just to serve what we consider to be basic, baseline load growth. That amount of capacity that's online by the end of our forecasting horizon increases very significantly when we look at the decarbonization cases, both the 80 by 50 case and the 100 by 35 case. What we're seeing is in order to meet those decarbonization goals on the power side, there's a ton, as you would guess, a ton of wind and solar capacity that's being added, and then also in particular in the 100 by 35 case, some flexible carbon-free generation that's being added to the model as well. And when we get all the way to 2050 in that 100 by 35 case, what we're actually seeing is the amount of capacity that's online in 2050 is 3 times the amount of capacity that's online in 2020. So a very significant build out of generation capacity would be needed to satisfy all of the requirements of these decarbonization policies in the power sector. Given all that capacity that's going to need to be added to the system, then the question is, well, what will that cost? And so what you're seeing in this chart is just our estimate of the annual cost of building and maintaining and operating the bulk power system in the reference case and the 2 decarbonization cases. So in the reference case, just to kind of orient you on the chart, what you can see is in 2030, we're estimating that the average annual cost of running the system in that year is about $136 billion. That increases in real terms to $216 billion by 2050. If we jump all the way to the 100 by 35 case on the right, what you'll notice is that those costs are pretty dramatically higher. In particular, if we look at the 2050 bar, you can see that the annual cost of building, running, and maintaining a carbon-free power sector in 2050 is more than twice as high as it was in the reference case. So there's a very material incremental cost that we're estimating that is associated with decarbonizing the power sector. Just when we focus on power generation and transmission. This analysis doesn't even include the additional costs that would be associated with the distribution system. So that just gave you a sense of kind of how things are changing in the power sector in the absence of all of the new innovative demand side initiatives and measures that Jared and Avon described. So the question that we really set out to answer here is, how can those demand side measures reduce that incremental cost that we just characterized on the previous slide? And there are basically three benefit categories or avoided cost categories that we're looking at with that analysis. The first is the ability of energy efficiency and demand flexibility to reduce electricity generation variable costs. So the fuel and the variable operations and maintenance costs associated with running the power plants. We're forecasting those costs with hourly granularity using GridSim. We're also looking at the extent to which these measures can reduce electricity generation fixed costs. So that's the actual investment in generation capacity and then ongoing fixed O&M that is driven by growth in demand and also clean energy requirements, which we're forecasting in the model. And then the third cost category is reduced transmission costs. So this is the potential for these demand side measures to defer investment in the transmission system through load reductions. And in our model, Avon mentioned the fact that we have the 25 region granularity in how we're representing the US system. Our model allows transmission capacity to be added to connect those 25 regions. And if adding transmission capacity is a cheaper way to bring carbon-free electricity into a region than building it locally, that logic or that option is incorporated into our model. So a portion of the avoided costs that we're representing here are in avoiding transmission costs at that fairly coarse level of representation. So now what we're showing is the incremental cost of decarbonizing the power system in the gray bars, and then in the blue bars, the amount of that incremental cost that could be avoided through all of these demand side measures that we've just been discussing. So if we just focus on the right half of this slide, what we're showing there are those results for the 100 by 35 case in 2030 and 2050. And so what you can see if you just look at the first gray bar is relative to the reference case, the incremental cost of meeting the 2030 decarbonization requirements in this scenario in the power sector is about $56 billion per year. And what our analysis is suggesting is that about $25 billion of that incremental cost could be avoided through the demand side measures. And then looking out to 2050, there's an incremental cost of over $300 billion per year relative to the reference case. And about a third of that, $107 billion per year, could be avoided through these demand side measures. So that just kind of puts in context the magnitude of the opportunity or the potential that exists with these demand side measures, and also gives you a sense of what will be ultimately left on the table if we focus exclusively on kind of inefficiently and inflexibly electrifying the power system without also incorporating efficiency and flexibility into that planning decision. So now what we'll do on this last slide that I'm going to present is just drill down a little bit deeper into those blue bars that were representing the cost savings associated with the demand side measures. And basically what we're showing you here is how those blue bars break out across either end uses or customer types. So if we look at the chart on the left, just for simplicity, if we focus on the right-hand bar in the left-hand chart, what we're showing there is that, again, that $107 billion of annual cost savings associated with the 100 by 35 decarbonization scenario in 2050. And if you look at that chart, what you can see, this is breaking out how those cost savings, where those cost savings come from in terms of end-use efficiency improvements. What you're seeing is that this mirrors pretty closely some of the energy savings potential that Jared and Avon had presented previously. A lot of the opportunity that we're identifying for cost savings is coming from HVAC and envelope improvements, and also from water heating improvements, including introducing flexibility into electric water heating consumption. Those are the primary drivers from the end use perspective. And then if we look at the chart on the right, what we're noting here, again, paralleling what Jared and Avon had shown, is that a lot of that potential exists within the residential sector, and it is spread out in meaningful proportions across energy efficiency, more efficient electrification, and also the introduction of flexibility measures. So really, I think when we completed this portion of the analysis and stepped back and asked ourselves what it all means, to me, the biggest takeaway more than anything else was we can decarbonize the power system just by electrifying everything, but that's going to be an expensive approach if efficiency and flexibility aren't the first consideration when we're developing those plans. And my expectation is that we're going to start to see a lot of regulators and policymakers looking for efficiency and flexibility as part of any utilities electrification proposals going forward for this exact reason. But I will stop there, and Jared, hand it back to you to wrap things up.
All right, thank you, Ryan. And yeah, just want to take a few minutes at the end here to talk about how our data could be used going forward, and then just some musings on some of the additional areas for improvement, and then we'll get to about 10 minutes of questions at the end here. Excuse me. So I think the best way to access our data is through this landing page, buildings2050.lbl.gov. All of our key findings are kind of highlighted there. The interactive graphics that Avon mentioned are linked there, and then the actual study itself, which is published in the journal One Earth, and there's a DOI listed here, is also going to be linked at that site. We also have a Mendeley data record, which has a lot of really detailed data for our tables and figures. It also has a lot of the actual raw kind of modeling data that you could potentially use to kind of rerun or customize some of what we did. And we are actually trying to do that ourselves in additional work that's listed on the right here. So many of these different initiatives are using the scenarios that we've already built and kind of customizing or reworking them to different modeling needs. And we see that as kind of a key accomplishment from this study, is that it established a really solid data set that we can build from in improving the representation of buildings and demand side measures in buildings in energy system modeling going forward. And then lastly, this was a couple of years of modeling work, and we really learned quite a bit about the limitations in our models as we went through this process. So we just listed a few of the ones that came to the top of mind here, and I'll go through them briefly. I think one of the key ones is in modeling end-use electrification adoption. End-use electrification is right at the center of every discussion of building decarbonization, and yet we still understand so little about how consumers actually make those decisions, and we lack some of the data, I think, needed to get more granular, regionally granular with some of the factors that might go into that decision. So that's going to be an exciting area to watch going forward with some of the new policies and data sets that are coming down the pike. Coupling of building grid modeling. We have kind of a loose coupling here. We're incorporating emissions factors from the grid modeling on the buildings in the buildings model, and then we're also incorporating load shapes from buildings in the grid modeling. But I think going forward, we can make that a tighter coupling, and for example, kind of endogenously compete demand side measures in the models like GridSim and the capacity expansion modeling that's being done for the power sector decision making. Representation of demand side flexibility. We built off of previous work to represent that in this study, but I think We can be more dynamic in the way we look at responsiveness to different price signals and more sophisticated schemes for procuring flexibility from the building sector going forward. And then lastly, accounting for additional building emission sources, in particular refrigerant leaks and embodied carbon across the full building life cycle. I will note that we did deal with refrigerant leaks to an initial degree, and I'd encourage you to look through the discussion section of the paper, where we tried to trade off the emissions impacts of these refrigerant leaks against some of the benefits of reduced leaks in the natural gas supply emissions. So that's actually something that we're looking at quite closely, and we'll see more on that in the near future. And with that, I will say thank you so much for your attention, and thank you to all my colleagues here for the study, and we look forward to your questions.
Great. Well, thanks, Jared and Avon and Ryan. Excellent job presenting the results. As is always the case, we probably have more questions than we have time for, but I wanted to hit a couple of the high notes here, just ask some questions to each of you. Maybe Jared, I'll start with you. Sort of just for folks maybe new to building simulation, building modeling in general, how much do the measures and package assumptions sort of the results that were in this study represent real world energy savings, or sort of to what extent do we perform reasonableness checks on these results to make sure that they're somewhat empirically grounded?
Yeah, well, that's a good question. I think that, we start with a foundation of measures that are based on, real kind of equipment performance data and performance characteristics. And we do look at the kind of unit level savings impacts of representing different levels of performance. I think that where we get into more speculative territories with some of the perspective measures, these kind of breakthrough technologies that we represent coming into the market later, which are hard to forecast, but I think important because they do have impacts in terms of the cost effectiveness with which this is achieved, and have important impacts, of course, on the depth of energy and emissions reductions that we're able to get. So we rely on a number of different data sources for the measures that we defined. We did link to the measure definitions here for those who are interested in going into the kind of nitty-gritty sources that we used to try to characterize realistic performance levels and the evolution of those performance levels over time. The other thing I'd say is that we're increasingly trying to benchmark the projections that we're making against kind of historical trends in building sector energy use and emissions, and also kind of lower level trends. For example, in heat pump sales, I showed a plot that was trying to do that. And I think that's going to be something that we need to do even more going forward, because there really hasn't been a lot of good data that we can, or at least kind of commonly used methods for tracking and benchmarking some of these projections. But that's something that we'd like to focus on going forward.
That's great. Thanks, Jared. Ryan, there were a couple of questions that came in just asking about sort of where is distributed generation in the power sector modeling? Did it appear in the portfolios that you modeled? And if not, do you have any sense or any guess, what is the role of distributed generation in this future that you modeled?
Yeah, and I think that looking at that question at a very detailed level would be a great extension of the research. Jared teed up a few ideas at the end there. I think that would be another one that would be great to dig into, is efficiencies or kind of integration of distributed generation with these other demand side measures that we analyzed. It appears in our modeling at a high level in the sense that we did exogenously include some adoption of distributed generation in the modeling. We didn't solve for the economically optimal amount of distributed generation adoption endogenously within the modeling, because that is in a sense, that is a very different economic question than how do you sort of minimize the cost of building out utility scale resources, right? Consumer adoption of rooftop solar has a lot to do with the retail rate and what retail rate that customers facing, net metering policies, local incentives, and also just behavioral questions around customer willingness to adopt distributed technologies. That was, I think, more than we could take on in an analysis that was primarily focused on decarbonizing kind of the utility scale power sector, but would be a great, like I said, great kind of next step in the research if we were able to.
Yeah, no, great idea. I like that. So Avon, just a question. I know you had sort of initially answered this one in the Q&A box. Someone had asked about the incorporation of IRA and bill and some of these substantial federal policy supports. I know you've been doing some work in that area. We didn't incorporate it explicitly into this analysis, but have been doing some work. Do you have any sense of the scenario among the scenarios that we modeled, which ones might match sort of closely to our projections or other folks' projections on the IRA and bill impacts?
Yeah, that's a great question. And we have been doing some follow-on work here to reflect some of the incentives and policies that are that we see in IRA and bill and the impact of those on the building sector in particular. I would say that kind of our initial modeling shows that the impacts of those policies are kind of in the, I would say maybe kind of between the low and the moderate case that we represent. So, certainly there's definitely an increase in building electrification that we're modeling as a result of some of those targeted incentives. But really the kind of the rates of fuel switching that we are representing in those more aggressive decarbonization cases are, at least in our opinion, kind of not likely to occur just under the types of policies that are available in IRA and BIL, and would probably require some more additional support to reach those levels.
Yeah, that's great context setting for maybe some future policy discussions as well. I guess in the last remaining time, I want to kind of do a round robin. So I'm going to ask each of you the same question. I'm going to channel one of the earlier supporters of this work, Monica Newcomb, and just ask each one of you what surprised you the most about the study findings. So we'll do a round robin here. Maybe Jared, I'll put you on the spot to start with, and each one of you can share just what surprised you most about these study findings.
Honestly, I think the depth of both potential emissions reductions and the power system impacts kind of surprised me. We did a study a few years ago that was looking, at least on the emissions impact side of things, that was just looking at the 80% by 2050 target that the mid-century strategy had laid out at the time, and looking at compatibility in the building sector there. And we were struggling to get to 80% at that point, and a lot of that was because there was not quite as much representation of some of these policies on the demand side, and then on the grid side especially, the projections were much less rosy. And now we're looking at much more aggressive power sector decarbonization scenarios. So it's really interesting to see how that has affected how that's changed the picture for building emissions reductions. But at the same time, that even with the changes on the grid side, that you still need much more aggressive deployment of demand side measures to get to those deepest levels of emissions reductions. So that to me was surprising and kind of interesting to work through in the modeling.
That's great. Ryan, I'll call on you next. What surprised you most about the study findings?
Yeah, kind of, I guess, picking up where Jared left off, given the depth of energy efficiency and flexibility that we were modeling here, I was surprised to see how much of that was economic or cost effective in our modeling. I think you can always model very aggressive efficiency improvements, but the question is, at what cost will that come? And does it make more sense to do that than just going out and building another wind farm? And I didn't get to this in my comments, but what we found was the vast majority of this portfolio of resources is cost effective and has costs that are outweighed by the benefits. And to me, that was a pretty impressive takeaway, and really suggests that there are other non-economic barriers that we need to address in order for what we've laid out in this presentation to materialize.
Yeah, that's great. And Avon, we'll have you bring things home. What surprised you most about the study findings?
Sure, maybe I'll speak to kind of a more specific case on the demand side, and looking at the impact of early retrofits versus kind of the regular replacement rates. So we model both in our analysis, and I think in the building decarbonization community, there's a lot of focus on the importance of accelerating early retrofits. And I saw some comments in the chat to that nature. And while accelerated early retrofits, which we do model in several of our cases, do have an impact, just given the kind of the long time horizon that we're looking at, there is ample opportunity to make use of kind of regular replacement rates in order to facilitate building sector decarbonization. And so, I think kind of the takeaway there is that while early retrofits definitely are important, really getting the replacement decisions correct is more important in the long term in terms of achieving these longer term pathways and the deep emissions reductions that that we show. So, thinking about how that connects to consumer decisions around replacing appliances at the end of their lifetimes, those sorts of replacement decisions are really responsible for the bulk of the emissions reductions that we're seeing. And so, there are others who definitely espouse the strategy of trying to get those decisions right and make the right choices and enable consumers to make the right choices with those decisions, rather than necessarily needing to do all of these early accelerated retrofits. So maybe that's a bit more in the weeds, but that was something that surprised me.
That's great. Well, we've reached the end of our hour. I certainly want to thank all the attendees for joining us, and we certainly invite you to visit the study website and explore our findings in more detail. Certainly feel free to contact the study authors with any follow-up questions you have, and we look forward to sharing our future work on building and power sector decarbonization with you all. So thanks again, and have a nice rest of your day.